Yes. Hi, hello everyone. Good evening to one and all. So, yes, of course, APSSDC again conducting one more webinar for you. I hope you all of us know we are conducting many webinars and many training programs. And so today it's like the topic was different. I think it was this webinar, what we are doing now, we didn't done in before. So that's why it's like the topic and everything was new webinar. Just I'll share the screen. I'll show the poster regarding what the webinar on. So smart mobility and advanced driver assistance systems. So just listen what they are saying. So just observe, and if it is definitely, I think it was useful to you. Just learn and utilize in your career. That's what I can say there. Of course, you all of us know my name is Haripriya from APSSDC. So now I would like to introduce the speakers of this program. So Ayush and Arjun. So both are from AKAR International companies. I think Ayush was the co-founder. So I think Arjun is also uh, he was also giving guidance and career guidance and what the career in this ADAS. So just observe, just listen and utilize and ask the doubts regarding this topic, and definitely I think just make use of this webinar. So and Ayush, just start the session, and Arjun, you also after forward to Ayush. Thank you so much.
Thank you. I think it's better everyone can mute their mic so that there is no disturbance.
No, others cannot unmute or mute their mic. Always they are unmuted only. So they are muted only. So
Okay.
because the only speakers can talk in air mute. So this is this facility. Others cannot talk. Once they raise the hand, then only they can talk. So
Okay.
disturbance, I think, from our side only. But audience not.
I think now there is no disturbance.
No, no, no. It's very clear.
Okay. So can you see my screen?
Yeah, of course, very clear. The screen was.
Great. Okay. So welcome everyone. Sorry for the delay, and I shall start now the presentation and the webinar on smart mobility and ADAS systems. If you have any questions, you can type in the chat, and then we will, after the session will finish, then we can have the discussion session and the Q&A platform. So, uh, yeah, so good evening, everyone. My name is Ayush Maheshwari. I am co-founder at AKAR International. It is a Singapore-based firm which works in smart mobility and ADAS domain, specifically in the education uh, area. So in this webinar, we will be first talking about our company, then we will be talking about smart mobility and ADAS systems. Then I will give you a high-level view on control systems, which is a core heart of designing ADAS algorithms. Then we will have a high-level view on lateral dynamics. And further moving on, I will be talking on the system engineering and ADAS architecture. And then we will be showcasing our product simulator on cruise control, which is already blended with our webinar as well as seminars. And then we will have our discussion and open to Q&A. And if the time is left, I will be also showing some high-level view on vertical dynamics. So first talking about AKAR, it is a Singapore-based company which was co-founded in 2012, and AKAR provides its products and services in two verticals. So we started with fintech and software engineering, which is for our first vertical, and our second vertical, which was started in 2017, is in the domain of automotive and smart mobility. This webinar on smart mobility and ADAS system is presented by AKAR team in collaboration with Andhra Pradesh State Skill Development Corporation. And I would like to thank them for giving us this platform to share our knowledge with everyone of you. So for the presenters for today is me and Arjun. Unfortunately, Ram is not available for today, so he will not be joining this seminar. And I did my master's in automotive mechatronics from Cranfield University. Earlier, I had worked with Honda R&D in vehicle dynamics division, and then after my master's, I worked as a research and development staff with Cranfield University. And Arjun did his master's from Oxford Brook University in automotive engineering and specialization in electric vehicles. And currently, we are doing our professional doctorate in engineering in automotive systems design at Technical University Eindhoven, Netherlands. So our framework model, AKAR, focuses on designing an ecosystem in India where all the government organizations, universities, corporate sectors work together in a synergistic ecosystem for the development of smart mobility and ADAS domain in India and in transportation sector in India. So talking first about our products and services, we provide online courses, webinars and seminars, as well as online courses which are equivalent to your UGC programs. And the online courses are based on advanced automotive engineering courses. Then our online courses are supported by our EdTech product, which is Automotive Educational Kit for the blended learning. We will be showcasing one of our product in today's webinar. Then we also support corporates as well as universities in developing the Advanced Automotive Lab, or I shall say Center of Excellence, for the vehicular system and implementing model in the loop, hardware in the loop, and other functionalities which are quite important for development of ADAS systems. And then last not the least, we also provide technical consultation in ADAS product development to formula student teams as well as to competitive teams in universities. This is one of our theoretical sample content of a 6-hour seminar where we focus upon control theory, vehicle dynamics, as well as ADAS development. So we provide these online courses where we try to cover from basic fundamentals, starting from linear algebra and vibrations, and then eventually covering the control theory, and then the vehicle dynamics control part. And then in the last, we talk about ADAS architecture. So this is our specific template for our online courses. Along with our online courses, we are also developing the simulators, which when blended with the online courses, you can perform various experiments, what you are learning parallelly. And some of these experiments I will be presenting over here. So our first experiment is the cruise control system, which is developed with Unity Game Engine and MATLAB via wireless network. This system has been developed by Arjun and Ram, and the subjects covered in this particular experimental bench is vehicle dynamics, control systems, state machine, and C sharp, programming via C sharp. So basically, Unity Game Engine, the programming is done in C sharp. And then there are sub-experiments and the additional hardware. So we will go in detail specific to this particular experiment bench in the later phase when Arjun will be showcasing our product. Our other products are vehicle trajectory controller, which you can control by Logitech steering system. This is still in the development, and again it is developed with the use of Unity Game Engine and MATLAB. And then we have our replay model for ride and handling control, where we cover the subjects of ride comfort analysis, handling analysis, GUI interface development, and programming via MATLAB. So our experiments and online courses try to provide specific knowledge in a particular domain which is required for development of ADAS systems if you are working in the corporate or if you will be switching from university to corporate in future. So in 2020, we collaborated with Automotive Research Association of India, ARAI Academy, Ministry of Industries, and then we also collaborated with MathWorks India in this year and ANSYS India. So our seminars which were taken this year were supported by MathWorks and other seminar was supported by ANSYS. Now I will start giving you the high-level idea of what smart mobility is and what are exactly ADAS systems. So today, if we talk about the bigger picture, we have seen that today many applications in today's world, such as aerospace, robotics, automotive, defense, have developed smart systems attributing to the increasing power of computation. And there has been quite a industrial revolution now when we say industry 4.0, which is used interchangeably with fourth industrial revolution and represents the new stage in the organization and control of the industrial value chain. So industry 4.0 is comprised of the cyber physical systems which are developed from the multidisciplinary domains, and they form the basis of our smart machines. They use modern control systems, embedded software systems, Internet of Things, machine learning, etc. So in 18th century, we started from Industrial Revolution where we were uh, introduced, the world was introduced to mechanical production machines powered by water and steam, and today we talk about cyber physical system. And as we have moved towards the industry 4.0, the level of complexity has also been increased. So when I say smart systems, what exactly I mean by smart system? So smart systems are those systems which show these three attributes. So first is the control and monitoring. So my system should be able to monitor its own operation as well as external environment. Then communication and interconnections. So system should have a capability to communicate with other intelligent agents. And then the intelligent decision making. So system should be able to make an optimal decision and customize the user experience. So a particular smart system can vary on various levels. So a simple smart system can have just a control and monitoring attribute, while a fully developed smart system can have all of these three attributes. So we try to use the technology to embed all these attributes into a particular system. Now, when we talk about automotive domain, smart systems in the automotive domain, we need to define the various levels. And these levels are defined using SAE Taxonomy, which is defined by SAE J3016 level of driving automation. Why we have developed this sort of a chart is this new chart offers more consumer-friendly terms and definition for the levels which are frequently referred by the industry media. So this infographic will help in eliminating the confusion and providing more clarity across the automotive community. And it also helps in standardizing the framework across global automotive companies. So it got engineers and other people working behind the development of these smart systems. It provides the benchmark and the scope to their development. So there are 6 levels of automation, starting from level 0 to going till level 5. And over here, we have option of what does human can do in this level and what does my intelligent vehicle controller can do, and how they are going to optimize the decision making between human driver and the intelligent vehicle controller. So when we talk about level 0 over here, my intelligent vehicle controller has a limited features, which is like providing the warnings and the momentary assistance. So we can see in today conventional vehicles that there is automatic emergency braking or blind spot warning or lane departure warning. So these are the examples of level 0, and these features are providing the assistant to human driver. But most of the time, actually all the time, human driver is driving the vehicle. But when we move to level 1, these features provide either the longitudinal assistance or lateral assistance. It is important to note over here that one of them is presented, the longitudinal or lateral, but not both. So I have a sort of a lane keeping assist or adaptive cruise control, but not both. So again, in this feature, human has to maneuver in most of the conditions, but in the case of lane keeping or adaptive cruise control, depending upon the vehicle, human can depend upon the intelligent vehicle control. Now, when we talk about level 2, so these features provide both longitudinal as well as lateral assistance to support the driver, which is lane keeping or lane centering and adaptive cruise control. So in the level 2, human can take support from intelligent vehicle controller for or adaptive cruise control or lane keeping or lane changing. So from level 0 to level 2, we can see that there are limited assistance which is provided by the intelligent vehicle controller, but the complexity increases as we move from level 0 to level 2. But when we talk about level 3, so over here, human is not driving when these automated driving features are engaged, even if you are seated in the driver's seat. And in level 3, there will be some conditions or some environment where the intelligent vehicle control can't perform the maneuvering. So over there, it requests human driver to take the control, and then human has to drive the vehicle. A typical example of this is traffic jam, a chauffeur, or we can say in a controlled environment, remote valet parking. It can be considered as an example of level 3. When I talk about level 4 now, so these automated driving features will not require you to take the driving, and the examples of these are local driverless taxis, and or the pedal and steering wheel may not be installed. So this is a particular example of level 4. So these features will drive in most of the conditions and will not operate unless all the required conditions are met. So this is quite important thing to know over here, that all the conditions should be met, then only the intelligent vehicle control can take the authority. And in the level 5, we have a full functional vehicle, which is equivalent to the human driving. And this feature can drive the vehicle under all the conditions. So the difference between level 4 and level 5 is that level 5 is same as level 4, but feature can drive in all the conditions across the environment. So this is quite important to understand the taxonomy and the definition for the terms related to on-road motor vehicle automated driving systems, as it will help you to define your scope while developing your product. Now, as we have seen that what are smart systems and what are the level of complexity in these smart systems, so how should I decide at what particular point I need to stop? What should be my abstraction level? So there are various attributes. So one is the demographic and the customer base. What exactly is the requirement from the customer end? Then what is the system developer knowledge? So if there is a lack of domain knowledge, then you will not be able to develop the fully functional smart system. Then the competitive positioning of a particular OEM, which is designing this smart system. And then, of course, the country's infrastructure. Because as we have seen earlier, that a smart system has also an attribute of intelligent vehicle communication. So if we want our vehicle to communicate with my infrastructure, then country's infrastructure should also support it. So over here I have taken an example from the agro tech. I have a particular conventional tractor and I want to make it to the smart system. So first I am putting a controller design into it and I'm trying to perform the maneuvering from the intelligent vehicle controller. It may be lane changing or it may be cruise control depending upon the requirement of the OEM. And then on the third level, I also wanted to connect with my smartphone. So I need a particular communication protocol to connect it with my smart product or smartphone. And then once the tractor is communicated as well as has an ability of monitoring its environment, so monitoring is coming from the controller and the interconnections are coming from the communication with the other smart agents. And now I want to further integrate it with other farm equipments. So I need more level of complexity. And then it can be further part of a bigger system where I can have a weather forecast, speed optimization system, irrigation system, farm equipment system. So this is a particular example, a case study I have taken from the Harvard Business Review. And of course, the sky is the limit, but we have to decide that how to define my system boundary, which set of smart connected product capabilities and features should company pursue, and where I need to stop. So now I will move further on the ADAS system. So first we had talk about Industry 4.0 and smart systems. Then we talk about various level of functionalities in the automotive domain. And then we talked about abstraction level. So it's very important to understand this process flow to understand and have a good understanding of ADAS systems. So ADAS stand for Advanced Driver Assist Systems, which are electronic systems that help the vehicle driver while driving. So there needs to be a optimal control authority between the vehicle driver and the intelligent vehicle system. So what are the features ADAS provides? It has an ability to sense its environment. Based on the control algorithm, it has an ability to process or think. Then based on the algorithm, it will further perform a particular action via actuators, and then it will communicate it to the human. So it's very important to create a optimal human machine interface so that there is a synchronization between the vehicle driver as well as with the intelligent vehicle system. If there will be no synchronization, it might lead to safety issue and or accident. So modern day vehicles are seen as a perfect integration of numerous systems, each of which varies in intelligence and basically all interact and overall controlled by the human. When I talk about what is the need of ADAS system today or what is the need of smart mobility, we can see in India that a lot of work has been done by government on electrification and hybridization, and they aim to achieve electric vehicles by 2030 on roads, and they're also developing the infrastructure for that. But right now, smart mobility is not much focused, but it will be a focus in upcoming future. And hence, what is we need to first find what is the need of ADAS system. So we can see that across the globe, there are sort of peak hours spent in the congestion during the traffic, and the index congestion rate is also quite high. And we need to understand in India also the traffic is not that seamless in metro cities like Delhi or Mumbai, and smart mobility can help us to achieve that. Now we need ADAS systems and we need smart mobility. And we can see also that technology and innovation in Netherlands is ranking 4 in this, and United States is in top 1. So India comes quite low in that score, and which is 0.54 in technology and innovation. So there is a very need to have a knowledge of ADAS systems the domain knowledge to develop these smart mobility. So I would like to give a bit of focus on this chart, and we can see that there are the total score is sort of dependent upon the policy and legislation, technology and innovation, infrastructure, and the consumer acceptance. So we need to understand all these four attributes while designing our smart product. Now I will talk about how OEMs are focusing upon the ADAS technology across the globe. And we know that driving is quite a complicated task, which requires significant level of expertise and experience. And a lot of research, lot of research focus is also put into making this fully autonomous vehicle navigate in the complex and challenging driving scenarios. So ADAS systems take care of some critical aspects of driving depending upon the SAE level. The examples are SatNav or TomTom, which helps in suggesting the route to the driver. Adaptive cruise control helps in maintaining the speed to give driver the perfect balance of braking and acceleration. And with a better and more perspective, sensory percepts, we can have a faster rational decision making abilities. So smart mobility is today used by almost all the OEMs, Land Rover, Ford, Honda, BMW, etc. And they are trying to create a whole ecosystem of ADAS technology. So this is an example of a highly automated driving, taking care of the lateral and the longitudinal system. And you can see over here that different sensors are used for different type of ADAS algorithms. Long range radar is used for adaptive cruise control, and the ultrasound are used for the parking assist. And for cross traffic alert, the short medium range radar is used. And for the surrounding view and for traffic sign recognition, we use camera. So there are different types of sensors which are used to develop these ADAS systems. So first we need to understand what is the pipeline, what is the flow of ADAS system architecture. So the primary components in an ADAS system is sensors, processors, actuators, and software algorithms. So, and other features you can of course add it over these components to make it much more complex system and providing the high comfort to the user. So sensors will first perceive the external data. They will send that data to the software algorithm. Based on the software algorithm which is running on the processor, it will make some decision and it will send those commands to the actuator, and then the actuator will perform a particular action and will also inform to the human driver. And then we can have secondary components like connectivity, where you can have a vehicle to vehicle communication or vehicle to infrastructure communication. You can store your data into the data cloud, and you can use that data further to study your driving statistics. And then there is middleware. So if there are a lot of ADAS algorithms running in the system, we need and if they are dependent upon each other and have a high dependency between them, then middleware is used to basically perform a seamless integration between these software algorithms. So we can see over here what once were purely mechanical systems in the automotive domain 10 to 15 years ago has been now completely transformed into multidisciplinary systems over here. You have a computing over here, you have electronics over here, and the mechanical part is covered from the plant dynamics and the actuator. Then you have to study sensor fusion. So that's why we say that designing a ADAS requires some multidisciplinary knowledge. And if you have only knowledge in one particular domain, let's say vehicle dynamics only or powertrain only, then it is not sufficient to design a particular ADAS component. These are some examples of ADAS component over here. I can say LiDAR. Then as a processor, I have given an example of NVIDIA Jetson AGX. Of course, there are other companies like Texas Instruments, ASML, which provide these processor boards. And NVIDIA also have high number of processor boards depending upon your functionality. Then you have actuators, throttle, brake, and steering, and then your software controller. So over here I have given an example of YOLO algorithm, which is you only look once. It is a deep learning algorithm which is used for computer vision. So when I talk about the sensing environment, this is another form of ADAS structure. You have a sensing environment which further sends its commands to the actuators, and based on the software algorithm, actuator perform these commands and then send it to the vehicular system and interact with the driver. Over here also, depending upon the different type of algorithm, I am getting data from the sensors, which is getting the information from the environment. And further, these ADAS systems are sending the control commands to different actuation systems. So it depends upon which type of algorithm you are using, and then sending the HMI warning to the driver. So when we talk about ADAS verticals, there are many verticals, and it's up to you which vertical you want to choose. But in each vertical, you will find that you need a multidisciplinary knowledge. So vehicle dynamics and control, power electronics, computer vision and image processing, machine learning, deep learning, embedded systems, human-machine interface, software architecture, and there are some other verticals also. So it's up to you in which particular domain you want to enter. Eventually, you will find out that when you will be working in the company, you will be working in the integrated environment between these verticals. So this is a European roadmap smart system, and it displays how my ADAS is set up with respect to the level of autonomy. In the level 1, either I have a adaptive cruise control or lane keeping assist. In level 2, I have integration of both lane keeping assist and adaptive cruise control. In level 3, I have other features also acting into the system, making it much more smart and intelligent. In level 4, you have a lot of ADAS systems, and then you need to perform a proper sensor fusion. And then the level 5 is the decision making, which is machine learning and AI implementation. So this is a particular roadmap distributing the ADAS along the various level of autonomy. Now I will again give a quite bit of a recap. Then we started with the Industry 4.0 smart systems, and then we moved towards ADAS system, which are smart in automotive world. And then we talk about what is the importance of ADAS systems. And now I will talk about what are the particular domains which are required to have a good knowledge of ADAS systems so that you have a capability to develop ADAS algorithms. So if we talk about monitoring, which is one of the important attribute of smart smart system, we talk about control engineering. So how control engineering works. So control engineering helps in monitoring my reference input, and it also not only maintain the reference variable at the required values, but also allow the system to change it. So for example, if I talk about adaptive cruise control, then I want, or specifically, let's talk about cruise control, which is much simpler example. And I want my vehicle to drive at a constant speed of 70 km/h on the highway. So I can give authority to the intelligent vehicle controller where my reference input will go as 70 kmph, and then based on my control algorithm, it will try to maintain that speed on a highway until unless human takes back the control. And these control algorithms further are embedded in the microprocessors and can provide better control and automation. Now, when we also walk humans, how they monitor, we sense our environment via our eyes, and then our brain controls, understand the environment and sends our actuation to our limbs. So similarly over here, we need a feedback, like we are taking the monitoring from the environment. So if we manipulate any input variable, it will affect the change in output variable of a system. And then based on the output measurement, a decision is made by the controller and action is performed. So I will show a particular flow chart of control engineering in further slides. Now, moving towards control engineering, there are two domains of control engineering, two major divisions, which I can say classical and modern, and they have a direct implications over the control engineering application. When we talk about classical control theory, so my scope is limited to single input and single output design system, and the system analysis is carried out in the time domain using differential equations and in complex S domain with Laplace transform. So if you are from the mechanical background and doing your bachelor's, I suppose you would not have studied much of a control engineering. And I will be covering a high level view of control engineering so that you can get what is important for understanding the aspects of control engineering. Since this is a webinar, I can't go into in-depth detail of that. And PID closed loop is one of the common classical control theory architecture. Now, when we talk about modern control theory, we can deal with multiple input and multiple output systems. And the systems are represented in the terms of time domain. So I have a various ordinary differential equation, which I decompose into single ordinary differential equation and then write my system in the state space analysis using state variables. So all the systems are over here can have a multiple input and multiple output design. Then further in the modern control theory, you have various subdivisions, nonlinear control theory, multivariable control theory, adaptive control theory, and the robust control theories. Today, a controller designed using the classical control theory requires on-site tuning due to the design approximations. Yet, due to the easier physical implementation of the classical control theory, you will see most of the industrial applications today use or they prefer classical control theory over modern control theory. This is a particular example of a control application in the cruise control domain. Now my vehicle human has set up the speed of 70 kmph, and I am taking the output from my sensor, the vehicle speed sensor, and I am comparing that and calculating the error, and that error further goes into the controller, which further performs the control action and send the command to the throttle actuator to reduce the error to zero. The objective of the controller is to reduce error to zero. So supposedly I was driving at the speed of 50 kmph and I set up my cruise speed at 70. So it will take the output as 50, it will calculate the error, perform the action, and it will give a throttle actuation. Speed will increase from 50 to 60, error has been reduced, but there is still a non-zero error. Then it will take 60 kmph is an output from the speed sensor, will compare it with the speed error and will try to reduce the error to zero. Now it depends upon your control algorithm that how much accuracy is there. So again, when I say there is an abstraction level in the ADAS system, eventually I mean that your abstraction level depends upon the control engineering and which level of control strategy you have used, and based on that control strategy you will achieve particular accuracy. So if you will use a classical control theory, the accuracy will be a bit low, and if you will use modern control theory and robust control strategies, you will have a higher accuracy. But of course, it depends that whether it is required or not, because developing or using a higher control strategy also requires a better processor and is also more expensive. So one of the most important, some of over here in the audience will be students also who have participated in the Baha or Formula student teams. And one of the most important weapon for the race car teams is information. And the more information vehicle can gather and process, the more better judgment and the decision a driver can make. So university racing teams can use the concept of vehicle dynamics and control for their testing and data acquisition process. With the better development of processor boards, you can now they are economical also. You can buy NVIDIA processor board and you can also set up a very nice optimum human machine interface for the drivers. So that was the control engineering aspect, which we were talking about the monitoring part. Now we will talk about the plant model. What we are trying to control. We are trying to control a vehicle or plant. And to understand the vehicle or plant, we need to understand the vehicle dynamics. So vehicle dynamics plays quite a major role in development of these advanced driver assist systems. And it is further defined into three sub-levels of vertical dynamics, longitudinal and lateral. If I see from a driver or layman point of view, he is not an engineer. So the terms we use are ride comfort. For example, if you are driving over a lot of perturbations on the road, then your comfort, depending upon your vehicle suspension design, your comfort will vary. So that ride comfort is controlled by the vertical dynamics part. And I will not talk about motion sickness over here because that is a bit out of the scope of this webinar. And then we talk about longitudinal dynamics, the cruise control part, and the adaptive cruise control part. And the lateral dynamics when we talk about maneuvering, handling, rollover, and when we are driving the vehicle at a very high speed, how stable is my vehicle. So these are some important terms you need to consider while designing the vehicle dynamics domain. Again, as there was a level of abstraction in the control, there is a level of abstraction in the vehicle dynamics, and their integration set up the level of abstraction of the ADAS system. So mathematical modeling of these vehicle dynamic systems is very important, and your concepts of fundamental vibrations and vehicle dynamics should be quite clear. And you need to understand what level of abstraction modeling is required. You can have a quarter car model, you can have a 4DOF, you can have a 7DOF, depending upon your system, what you are designing. And I always prefer that you start with the easy model and then you move towards a higher complexity rather than directly starting from the complex models. And further, the representations can be linear or non-linear, steady or transient, and open loop or closed loop. So eventually my whole ADAS system is dependent upon my vehicle modeling and control theory. And eventually you will see that if I calculate the stakeholder map of my ADAS system, it is affecting everyone in the business. It is affecting customer, it is affecting OEM, it is affecting proving ground testing engineer, validation engineers, simulation engineers, architectures, and then the configuration manager or the software developer or the team who are designing the middleware. So this engine, ADAS system engine, needs to be designed very carefully, accurately, and properly. Then only you will be able to satisfy all the stakeholders. So this was this session of smart mobility and ADAS system. And now we can set up a 5-minute break and where you can share your questions in the chat option, and I will try to answer that. And we can also take a 5 minutes break. So we'll start again at 6 o'clock, and let's take 8 minutes break. In the meanwhile, you can ask me questions, and if you want to take a coffee break, you can take a coffee break too. Meanwhile, I also will try to show you one video. Okay, this one. So this is an example from Mercedes that you can see the level of automation over here. Yeah, so welcome back. Now we can start with further um, slides. So now I will be going bit. I will be covering the high level view of control system. What exactly is control system and how you can use it, how you can increase your knowledge in this domain. I will be also sharing some references. So yeah, let's study now high level view on control theory. So as we have earlier discussed that a control system is a interconnection of components uh, aim to achieve a desired state system response, and classical control theory is used for single input single output system, and the input output relationship represents the cause and effect relationship of the process. So we have different type of control loops. One is open loop and second is closed loop. Open loop you can see in daily life examples like electric dryer or in washing machine, where you set up a particular timing and the process is done, and once that timer is over, then irrespective of whatever the state of a particular cloth is it dried as you wanted or not, it will finish. So that is an example of an open loop. And in the closed loop, as I shared earlier, we take the measurement from the sensors from the output, do the comparison between with respect to the desired output response, and then my controller performs the control action. So the measure of output is known as a feedback signal, and the difference is known as error, which goes under the control algorithm, and the objective is to reduce the error. So classical control theory can be only applied to the linear time invariant systems. And what do I mean by time invariant means is signal will not change over the time. And with the linear system, I mean that it should be able to express mathematically the properties of multiplicity and superposition principle. So what do I mean by superposition principle is if I give my input as x1 and output I receive as y1, and then I give my input as x2 and I receive my output as y2, then the summation of input, if I'm given x1 plus x2, should give me the output of y1 plus y2. So that is what the superposition principle is. Then I talk about the multiplicity. So if I'm giving my input as x1 and getting my output as y1, and if I then scale my input with a times x1, then my output should be a times y1. So in real scenarios, most of the systems are nonlinear, which is the sources for the nonlinearities can be friction, backlash, saturation, or hysteresis. And for designing the control algorithm for the nonlinear system, the method is to build equivalent linear model. Arjun will go in bit detail when he will be talking about the linearization in our simulator, what we have designed, and where the nonlinear particular attribute was coming because of the aerodynamic equation, and then we linearized it into linearized equations. So nonlinear to linear modeling is quite important. You can see in the example of vehicle suspension also that bump stop, it provides the nonlinear graph. In nonlinear behavior, you will obtain majorly either analytically or experimentally. And how I perform the linearization is using Taylor series. So we perform the Taylor series across particular operating points where I want to linearize my system. So now if I see a graph over here, I can linearize it in across two particular operating points, one over here and one over here. Of course, operating points is dependent upon my control scope. Now, when I talk about control theory, how should I represent my system? So my system is represented using transfer function. Transfer function is basically used to particularly represent the Laplace transform of the time domain and Laplace transform of the input as well as the Laplace transform of the output. So the ratio between them is given by the transfer function. I have shown an example over here. Here's my spring mass damper system, and I have written a second order differential equation where u is my input and I want to log displacement y of a mass. You can see this in a real-time example as vehicle suspension over the roads. So the road input is force and the output is passenger comfort travel. So, or passenger comfort acceleration, which helps in calculating the ride comfort and the ride index. So I can transform my time domain to frequency domain, and any physical system can be modeled in a time domain where the response of a given system is a function of various inputs, the previous system values, and time. And as my time will progress, my state and the response will change. Why we perform this transformation from time domain to frequency domain is that time domain models for the system are frequently modeled using high order differential equations, which eventually will become impossible or difficult for humans to solve, and sometimes even for modern computer systems. Of course, it depends upon the level of complexity. And for example, if I talk about the control engineering in aerospace domain, then we have a lot of systems to control, and then there are really a lot of mathematical equations, and understanding in time domain or solving in time domain will be a bit difficult. So to counteract this problem, classical control theory uses the Laplace transform to change an ordinary differential equation in the time domain into a regular algebraic polynomial in the frequency domain. So you can see over here, now my system has been converted into a algebraic polynomial. And if I will go in detail, S over here is defined by sigma plus j omega, where my sigma is my real value and my j is my imaginary part, iota, and omega is on the y-axis, my imaginary axis. And a particular transfer function is represented by this, and the roots of this transfer function of the numerator are known as zeros, and the roots of the denominators are known as poles. So if I further go into the model control theory, then instead of changing the domains to avoid the complexity of time domain, we convert the differential equations into a system of lower order time domain. So if I have a lot of differential equation, a second order or an n order differential equation, I can decompose that into lower order first order differential equations. And it is important to select the set of state variables for the same. So state variables, these form the smallest set of independent variables. So you can write your plant in the term of transfer function. You can write in terms of state space. So state space is given by x dot equal to ax plus bu and y equal to cx plus du. So over here, x is my state vector, a is my system matrix, and B is my input matrix, C is my output matrix, and D is my feed forward matrix. So you can see also over from here, my input goes into B, which is BU, then it is added with AX dot, AX over here, and it gives X dot. So, and when I integrate my X dot, it is converted to X. So X dot is given by summation of A into X plus B into U. And when I talk about Y, Y is given by C into X plus D into U. And D is the feed-forward matrix. You can also convert your state space to the transfer function. If I have this state space system, and if I want to convert it into transfer function, so this is the step to do it. First, I take the Laplace transform of this, and then using the normal algebra mathematics, I can calculate my transfer function from this state space. So GS, my transfer function is given by C into Si minus A inverse into B plus D. Over here, the roots of the denominators are known as poles, which have a very important characteristic in defining the stability of a system. And the eigenvalues of A, which is my system matrix, are the poles of my transfer function. So in the seminar, which AKAR takes 9-hour seminars, we talk about how this derivation works and how you can actually see it in the real-time scenarios. Because of the length of the time over here, I am just giving you a high-level perspective. When we talk about the step response characteristic, and over here you can see that based on my step response, my desired step response will be something like, if I want to see my step change will be at a particular time and then it will go to 1, and this is how my controller is behaving. It first tries to goes in the transient state, and then it eventually reaches a steady state. And the step response characteristics helps me in defining how better is my controller. We have a rise time, we have a peak time, the settling minimum, settling max, and then the settling time. So how much settling time it is taken to achieve my desired response is defined by the controller characteristics. When I talk about the step response, it helps you to tell whether my system is stable or unstable in the time domain. For example, over here, this is a second order differential equation which has been converted to the transfer function over here. And you can see over here that my system is eventually getting dampened out. So my system is getting stable. So for example, if my vehicle is traveling on a particular surface, and eventually it will get stable out. But in the unstable system, my system is growing unboundedly. So this is an unstable system. And you can see that over here I have a negative sign in front of damping, which is not possible. But if you try to understand it mathematically, what my dampers do. Damper actually controls and dissipates the heat. But if my damper has a negative coefficient, it will give energy into the system, which will make my system unstable and grow unboundedly. So you can realize this in the terms when you can think of scenarios from automotive or aerospace domain. Specifically from the aerospace domain, there are a lot of examples of crash where the system has gone unstable. And then I have if I will remove my damping part, then I will be just left with the imaginary axis of the Fourier transform, of the Laplace transform, which is Fourier transform. So Laplace transform consider real as well as the imaginary axis, and the Fourier transform talks about imaginary axis. So this is a marginally stable system. This you would have studied in the simple harmonic motion during your high school. Then there are other responses also: impulse response, ramp response, and sinusoidal response. If you want to study about the sinusoidal response, I can share one example. When I was working with Honda as a proving ground testing engineer, we used to study noise and vibration in the vehicle, and we used to pass the vehicle over a various particular road profile comprised of sinusoidal inputs, and we used to study how much it is affecting my ride comfort. There are specific ISO documents which talk about sinusoidal input. And if I talk about from the handling perspective, your input is the steering wheel, and you can give a sinusoidal steering input, and you can see how stable is your car during the handling at high speeds. So these control methodologies helps you to define whether your system is stable and unstable. Then there is one body plot which is quite important to study, and it tells you how my system is going to perform the steady state response across frequency spectrum. So my transfer function is given by 1 upon ms square plus cs plus k, single over here as a spring mass damper system, and the magnitude of the complex number tells me the gain. So for example, my input is 5 into the system, and if I multiply it with the gain of 2, I will get 10. Simple multiplication. Similarly over here, this value will tell you the gain you will achieve at a particular frequency. And then the phasor angle tells you what is the phase lag between the input and the output. So this is a typical diagram of how body plot looks like, and it tells you across the whole frequency spectrum that how my system is going to behave. So over here you can see that in the lower frequency spectrum, input is almost equal to output. In the mid frequency regime, I'm getting a bit of a higher gain, sort of a peak, and then in the higher frequency, it is attenuated. And if you see an example from the spring mass damper system, over here, example. To explain, I will show you a bit of more like a demonstration from here, that if I have a spring mass damper system, let's say, since we are talking about body plot and steady state response over here. Over here is my input. You are controlling this, and I want to see change in my position when I am changing the input. So when my frequency is low, when you are just changing the signal very slowly, then the gain will be also a bit like same. From here we can see that. In the mid frequency region, if I will increase my frequency, system will actually have a higher gain, so it will go more than this. And in the higher frequency regime, if I give a very high frequency input, then my system will not change, my mass will not move. And there are a lot of examples from on YouTube from MIT where you can actually observe this phenomenon. So this is what Bode plot helps us to tell. So that's why the half power bandwidth is the point at which after which my whole output is getting attenuated, and which is approximately -3 decibel or cutoff frequency. The bandwidth concept also comes from here. And if I will change my damping, I can see the effect of change in my Bode plot. So this is a particular system and a control loop, a unity feedback closed loop. And my objective over here is to provide a good reference tracking, what I stated in the cruise control example. And then reject disturbances, which is basically if the extra disturbances are coming from the form of crosswind or gradient, and then attenuate the effect of noise, which is a sensor noise. So there are different particular terms which helps in defining this: sensitivity and complementary sensitivity. Sensitivity take care of the tracking and the disturbance rejection, and the complementary sensitivity looks after the noise attenuation. Of course, if you will attend our seminars, we will actually do the derivation of how we have achieved that. But if still you want to understand, you can take a complete understanding from the book mathematically, or you can see the video of Stephen Brunton, lecture on control bootcamp series. So it's quite a good series, and I will request you guys to watch this series to understand these concepts. I'm just giving a high level. Now, the pole location I was talking in transfer function, they helps me in defining how my system will behave. My system of a single differential order equation, something if I have like this, and you will see that if I use my exponential or sine, and if I take the derivatives of that, they are the recursive derivative. So that's why these are the solution for this differential equation. So that's how we achieve the concept of bounded case and unbounded case. Over here you can see if my pole lies on the real axis, you have a stable region, you can say over damp or critical damp. Over here your poles are lying in the left half plane, and you have a complex conjugate and it's under damping. And if they are lying in the right half plane in the complex conjugate, it's unbounded stable. And if it's lying over here, then it's increasing exponentially. So over here you can see it is an envelope of exponential and sinusoids, and this is just a sinusoid. That's why we define real and imaginary axis. And when we talk about just a steady state response in a Bode plot, we only talk about imaginary axis. So the stability of the linear systems can be determined from the location of the poles. So this is the roots of the characteristic equation of the poles over here, and your zeta value over here will define whether your pole will lie in a real pole or a pole at origin, in right half plane, left half plane, how it will depend. So the preferred topics to study from the references I will share later is these sort of stabilities, which will help you get a good idea. The best reference to study control system is from Professor Gopal from NEPTIL and NPTEL. On YouTube you will find his lectures, and they are really good, and I will prefer you guys to study those lectures in detail. Stephen Brinton covers it again on a high level view. I am covering on a very abstract level, but he covers on more of an intermediate, and then Professor Gopal lectures goes in depth mathematics of this. Similarly, we calculate our robustness over here using the gain margin and phase margin. And if you will see over here, my closed loop transfer function is gs upon 1 plus gs. And if I will put gs equal to -1, my system will go to infinity. So at -1, my system is getting unstable. So that's how I define my gain margin and phase margin. Then there are various control filters which you can study apart from PID, high pass, low pass, lead compensator, lag compensator, combination of these filters. and they help you in over here. These filters will come in the GC part over here, and they will help you in achieving your desired state response. Similarly, you can use PID controller. It is a proportional term which is directly proportional to the error. Integral term takes the integral of the error, the past time, and the derivative takes the derivative of the error, which is a future part. And on changing the KP, KI, KD, you can change the rise time, overshoot, settling time, and the step response characteristic. This is a particular example I've taken from the course of self-driving car optimization. You can see feed forward controller over here, and you can see feedback controller over here. So feedback controller provides the reactive way to respond to the error-based scenarios, and feed forward controller generates the actuator signal based on the predefined table. And if there is a sudden change in the reference velocity, this part takes care of the change in the error with respect to reference. But if there is a change in the reference velocity, then the feed forward controller is used to generate that signal. In summary, these are the specific decision-making parameters you need to take care of while designing the control algorithm. And the reference lectures, Brian Douglas YouTube lecture series, Stephen Brunton YouTube lecture series, MIT Open Courseware is quite good, and Modern Control Engineering by Ogata. These are quite good books if you want to study the control engineering. And it takes time and patience. You have to study a lot of mathematics. Fundamental of mathematics are very important to perform the in-depth study, because control system is technically all mathematics, and where the magic happens. And these online seminars and YouTube series can only guide you until unless you will not either do the experiment by yourself or perform the take the academic lecture from the university. So that's all on the control theory, and now I will give session to Arjun, and he will talk about the product, where we will be defining the ADAS part.
Yeah, Ayush, can you stop sharing so that I can share?
Yeah.
Can you see my screen?
Yeah, we can see your screen here.
Okay, so thank you, Ayush, after the theory what you've given. So now basically those theories which were said, now that needs to be applied in a practical terms. So the best way to learn is basically do a project. And what we've done is basically try to implement all this knowledge what we've gathered so far into designing and one of the part of the ADAS system, which is nothing but cruise control, which can be found in today's vehicles which are there. And this is developed by myself, Ram, and even Ayush. So what exactly we've done is, we've seen in cruise control, the steering wheel has got a number of options to set or basically operate the cruise control, basically to activate. So there are a number of buttons such as you have on button, set button, resume, cancel. So the basic operation of cruise control is exactly what? When you're driving on the highway and you want to stop giving accelerator pedal, brake pedal, and you want the system or the vehicle to take control so that you are peacefully sitting in the driver's seat and just using the steering wheel to maneuver, and the system is controlling all the speed or basically maintaining a constant speed when you're going on the highway. So here you come to a point where, while designing, when we were talking about the requirements or the use cases, what Ayush had mentioned, we've said that whenever the system is working and whenever the driver presses set button, the speed or the current speed of the vehicle will be incremented by plus 2 meters per second. And when you go down, it will be -1. So this design decisions is totally up to you as a designer when you're making a system. So keeping the product simple, user friendly, and also giving you a good intuitive feeling as to what exactly you're doing, the model what we've developed is basically when you go to a gaming center or a cafe, so basically what exactly you're doing? You're basically playing online games. So if you collaborate or merge that to the curriculum, what you're studying, that will help you give a much more intuitive feeling to exactly how the system is developing, and plus you learn extra as well. So what we've done is the keyboard which you have in your computer is an input source. So the buttons what you press is in the form of maybe acceleration, maybe selecting which mode you want to be set, resume, cancel, etc. And that goes to the supervisory controller, which is here, which basically decides which state the vehicle is in, whether human is driving it or whether the uh, vehicle itself or the controller itself in the vehicle is using it. It chooses this mode. Then it goes to the controller, which basically says, okay, what needs to happen is happening at the controller side. So it is controlling the speed, maintaining the speed, and any other disturbances which Ayush mentioned is controlled here in this controller. The most important thing here is, okay, fine, everything is working, but I would like to see what exactly is happening in the form of a video or in the form of a visualization tool, which here we've taken it in the form of Unity game engine, which basically shows you when you press buttons in your keyboard or when you're driving your vehicle or when the cruise control is on, what exactly is happening in actual environment. You do have to realize that considering the present COVID situation or considering autonomous vehicle, it is not possible or it is not advisable to track or basically test these systems on basically the live roads. You can't do that because you're testing and you don't know whether the system is actually working properly or not. So that is where these visualization tools come into picture so that you can test, validate, and then put your product into the real car and use it on roads. So this was a simple methodology what we've used. So what exactly is supervisory control? So you are driving the vehicle, that's a normal driving, human is driving. But when the system is driving the vehicle or taking the control, there needs to be a distinction between the person driving the vehicle and the system driving the vehicle. So supervisory control is a controller at a very high level which tells you or basically which indicates who is driving the vehicle in simple terms and layman terms. So to make this thing applicable in the software or in your understanding, there's a topic which is called as state machines, which other people also called as state flow. So basically it is nothing but going from one state to the other state. I'll give you an example in the next slide about it. Also, the fact that Ayush mentioned something about the architecture, you can have n number of architectures for this, but two most important thing what you need to take care is try to make the architecture simple so that it solves your purpose. And secondly, it should also be able to basically decode or debug the error what you're having. So if you make your architecture too complicated with a lot of input and outputs going here and there, it becomes very difficult to track what exactly is going on, what exactly is going wrong when you're testing it. So what we've done, we've just made one supervisory controller. You can have multiple, and basically this single supervisory controller is sufficient to basically handle the entire cruise control algorithm which is working on the system. Going into much detail, what we do is basically take the input. So these are the inputs from the button. So in the steering wheel, whenever you press the button, switch on, cancel, increment, resume, whatever it is, this input will be going in the form of, you can say, binary numbers, zeros or one, into the system, and you'll be getting a suitable output from it. Now, if I go in depth to what supervisory controller is actually doing, or what you call state flow state machine is, basically you are there in an initial state and you press a button on your keyboard as, for example, A. So this indicates it to go to another state which is called as switch on. Now the cruise control is running in your background, but you want your system to get actually activated and you want your cruise control to take over the control. So as a designer, what I say, I would like to only use my cruise control while I'm on the highways. That is, at least it should have a speed of 50 km per hour. So once this condition is satisfied, if I press the set button, it will come to the cruise control running state wherein I don't have to press anything. It is the system which is going to take control and do the necessary action. So this is a simple state flow which happens inside, and multiple things can be linked to it. So there can be a lot of interconnection. Here, after you see this diagram, you should appreciate what is the importance of having an architecture here? Because you can see there are a lot of inputs and outputs which are going. If you make it simple, it becomes easy for you to decode. That's why the architecture is important here. Moving forward, okay, you've designed the state flow. What next? The controller. But for designing the controller, as previously mentioned, there has to be certain boundaries, or there has to be certain specification that you need to maintain. My controller should be very fast, my controller should be very accurate, my controller should be very sensitive, etc., etc. So you need to set your boundary, because of course, when you make it very, very, you can say sensitive or very, very good or nice, or whether it is doing your purpose, it eventually becomes expensive, and also it becomes difficult because you need to incorporate a lot of theories and a lot of mathematics involved in this. So we've said, for example, the rise time should be less than 5 seconds, etc., etc. So we said for our development and optimum condition based on literature or the papers what we've got, like this should be the condition which our controller should be meeting. So once you have set your requirements, then you start coming and designing the controller. So how do we do it? Very simple. We've got an engine which is represented here, and we've got a nonlinear model. So the input to the engine is nothing but the throttle. What we'll be getting out from the engine will be the tractive force, which will be going to the wheels, and that would be coming as a velocity to that will be represented in the form of velocity to the vehicle. So why exactly we've mentioned it as non-linear? Because we know due to aerodynamic drag, which is half rho CdA V square is coming, it becomes non-linear. And also, since we don't have a proper engine map which says torque versus speed or power versus speed, we don't have that. So what best can you do with the limited amount of information what you have? We say, okay, fine, we know the maximum torque of the vehicle, we know the maximum RPM of the vehicle, and we know the ratio how it is split. So we define a torque characteristic curve here. Even this has a square term, so again this also becomes non-linear. So this entire system what we've made, it is in time domain, and it is going to work for the controller whatever you design. That's fine, but solving the system in time domain itself is not the solution. You even need to account for the different situations which which is happening, which can be represented in the form of frequency domain. So when we go next, now as it is, we've told you it's a non-linear system, and frequency analysis has to be done for linear systems. Now you said that from 50 kilometer onwards, I'm going to set my cruise control and I'm going to work. So there is a certain range. Of course, my top speed of the vehicle will be maximum, for example, 110 kilometer per hour or 120 kilometer per hour. Beyond that, nor my vehicle can go, nor do I want my vehicle to go. So you set a boundary there. So for all those velocities, what you do is take it as equilibrium points, and using Taylor series expansion, you linearize your equation which is described here for that particular velocities. So basically you're getting a single value of V. So for 50 you'll have one value, for 55, for 60, 65, and it goes so on. So basically you're linearizing for particular velocities and then analyzing the function in the form of a transfer function. So whatever transfer function you've got after performing a Taylor series expansion, for this you do all those things which were told in previous slides regarding Bode plot, and then you try to meet all the condition which was defined in the previous slide what I had mentioned regarding rise time, settling time, sensitivity. So this is the way the frequency analysis has to be done. Now even your frequency analysis methodology or the flow is good. I mean you have a brief understanding how this has to be done. What next? See, the controller is something which is not working in the vehicle continuously. When you're driving the vehicle, the controller is not working. So when you say the vehicle to take control, the most common thing or the basic understanding what you need to have is the controller should also know from where the control action needs to be performed. Of course, when the controller is not working, it is at a zero state. So whenever you press the controller button, it is going to start from zero and then go to the velocity or the cruising velocity what you've set. So there is a delay or a lag which is there, which you don't want. Of course, when driving a vehicle, you suddenly can't have your vehicle switched off for 1 or 2 seconds and then the vehicle starts moving by whatever you've designed. That's not practical, and that's not allowed also in terms of safety regulations and standards. So in that case, for the controller to know from which velocity I have to take the control action or basically maintain my cruising velocity, we've got something which is called as human machine interface, which we've represented here. So it will tell me, okay, from this velocity, I want like my controller to take control and maintain this speed throughout until and unless a human intervention or a plus plus or a minus minus button is pressed. Once you have done this, you've practically covered all the things which are required for you to maintain your vehicle in a cruise control state. So next thing what comes is testing. What exactly will you do in testing? So consider this as an example in which here when you see up till 25 seconds, it's the human which is driving the vehicle. Here we've got a cruise control which is working. Again, we don't have a cruise control which is switched off, and again the cruise control is switched on. So what happens is, for the first 25 seconds, we would like to drive our vehicle by ourselves, and once it has reached a certain velocity, for example 30 meters per second, I press the set button. This 30 meters becomes my cruising speed, and throughout the motion of the vehicle, it is going to maintain 30 meters per second. When I press the plus button, I would expect my velocity to rise by only 2 meters per second, because I have set it as a condition, and also the algorithm says only +2. So we can see here it increases by +2. Again, if you press and when you go down, it is -1. So here we see one state of your cruise control is working properly. There are a few more states that needs to be performing properly, which is cancel here, resume here, and then again pressing the set button again here. So once you perform all the operations which were mentioned regarding the cruise control, and then you see that your output or your application is performing properly, then you can say, okay, my controller is quite sufficient enough to handle the vehicle. And now next what I would like to do is I would like to visualize how exactly in an actual environment or an actual you can say moving scenario, how is this going to actually function, which we've modeled using Unity Game Engine. I would request Ayush to take control from here, and he will explain you about Unity Game Engine.
Thank you, Arjun. I hope you can see my screen.
Yes, yes.
So now this work was done by Ram. Since he's unavailable, so I will be taking the session on Unity Game Engine. So why Unity Game Engine? So Unity Game Engine is a very good tool as a cross-platform game engine, which is used for performing the visualization in automotive simulation virtual environment. And we can perform the ADAS simulations, and you can also use virtual reality and augmented reality. And for the coding, you have to do the coding in Unity Game Engine in C#. And how we have done is that, let's talk about the communication. Now the controller is running in a Simulink. Inputs are coming from the keyboard, and the visualization is done in the Unity Game Engine. So how I have connected the Unity Game Engine with the Simulink? So there are particular different type of protocols for the communication. This is also a very good example when you have to talk about vehicle to vehicle infrastructure communication or vehicle to X communication or anything. So we need to understand this communication protocol. So first, at the lower layer, we have Ethernet and wireless LAN, which is a link layer, like a wireless Ethernet cable you have, or router system, wireless router system. Then you have a network layer where you have a IP given a particular IP address, and then you have a transport layer. So TCP or UDP. So we have used TCP, and then different application layer. So how I need to send my data from one processor to another processor, and for that we have used HTTP. And there is a further REST API, R-E-S-T. I will write it in chat, REST API. We have used this for sending the data. So REST means you can post it, you can get, you can put, or you can delete. So there are different options over here. So the web server which we are using, HTTP, is also based on the REST API. And REST API is quite commonly used in the industry. Then earlier we started with the type 1 communication. We have one processor running both system, master and client. Then we switch to type 2 because this is more realizable, and this is how the ADAS system will also work. So if I have one particular ADAS system and other system, and I need to communicate it, and they're running on both on a different processors, how should I communicate it? So in our cruise control case, we are sending the vehicle velocity and mode input from the Unity game engine, and Unity game engine is further connected to with the keyboard system, and then velocity to be followed, and the control action output is given from MATLAB to Unity to visualize. This is somewhat the environment looks like of the Unity game engine. And these are the mode selections we have used for the keyboard systems. So this was our one of the product, and now I will show you exactly how our product looks like. So during using our products, you can use various experimental benches. You can change your controller. We have made it more of an open source, and you can see how the things are happening.
This is the demo video showing the working model of cruise control system that has been developed. Let's get started. At the very beginning, human drives the vehicle.
So controller, this is the controller
to a certain velocity, let's say more than 20 meters per second.
So this is in the Unity game engine, and this is controller is working in the MATLAB, and input over here are given from the keyboard.
And at this velocity, he sets the cruise control system on. As soon as he presses the cruise control system on, you can notice that the vehicle velocity has been settled to a reference velocity, which is now 24 meters per second in our case, and the vehicle continues to go at this velocity as long as the vehicle driver doesn't press anything. Now he can increase the set velocity by pressing set plus plus. You can see here there is a rise in velocity, which is 26 meters per second, and now he can still increase the speed by 2 meters per second by pressing set plus plus. If he wants to reduce the velocity of the vehicle, then he can press set minus. Now the vehicle velocity will be reduced by 1 meter per second, and he can further reduce from 27 to 26 meters per second by pressing the set minus. Now, if he wants to take over the control of the CC of the car, he can cancel the CC mode, and then, as you can see, now the vehicle is in control of the human. Human can do it, and then he can press resume. As soon as he press resume, the velocity of the reference velocity will be the same velocity previously where the system has been got cancelled. So it is 26 meters per second earlier. So it has come back to the same velocity. Now, human can accelerate this velocity, and as soon as he releases the accelerator pedal, so the system again takes control of the vehicle and make it run at the same previous velocity, which is 26 meters per second. Now human can brake control. He can drive it and make the vehicle to reach whatever the velocity he wants. And as soon as the vehicle reaches its maximum velocity, he can turn on the cruise control by setting it. As soon as he sets the speed after reaching the maximum, you can see now the vehicle speed has been set to 33 meters per second. So this demo covers all the use cases and all the modes of this cruise control system that has been developed. And thank you for watching.
So now you can see, so you can change these controllers, and you can see the effect, how it will affect our basically control effect on the plant, or you can change the plant also, and you can see what is the specific changes which are performed using the system. So now comes the last session of the day, which is system engineering and architecture. And I believe this will be quite interesting to you because till now we were completely talking about the technical stuff, and this is how ADAS architecture, ADAS systems are developed in the industry. You will be, you can, I will be talking on various tools which you should learn if you want to further pursue your career in this industry. So now we have seen that ADAS is comprised of so many domains, so many verticals, so many particular concepts. So there should be a particular methodology to design this system. I was talking about one cruise control thing, but in car you have supposedly 5 various ADAS sub-verticals and you have to integrate them. How you will do that? So we use system engineering method for that. So how the multidisciplinary system should be strategically developed? They should be first develop, test and validate. And let's talk about why do any project fails. Either the system is complex, there is an organizational issue, or there is a lack of knowledge. So there is one non-for-profit organization in COSE, an International Council on System Engineering, which has defined the system engineering methods, and it has been taken from the defense and aerospace because 20 years ago, defense and aerospace were the only domains where the multidisciplinary systems were used. So it is a formalized application of modeling to support system requirements, design, analysis, verification, and validation activities. And how model-based system engineering methodology helps? It helps in development of the multidisciplinary system seamlessly. It gives a bigger picture of how my system will look like. It will give you a better visualization, structured approach, continuous verification, and economical development. Now, 20 years ago, in 2002, 2004, I was talking to one of my friends who used to work in Suzuki. And earlier, how the prototypes were developed. If I want to do some change in the controller, or if I want to do some change in the car, I have to make a complete new prototype, test it, then observe it, then do the changes again, develop new prototype, testing, and it will go and go. It was a very long process and very expensive process also. But today the computation has increased a lot. You have a very good computation today. And because of that, you can apply the system engineering concepts in automated vertical also. So let's define what is a system. So before understanding system engineering, we need to understand how should I define my system. So this is a particular framework of the particular country. You have electricity, you have education, you have communication, you have transportation, you have healthcare, and so many bodies. And they are dependent upon each other. So we need to define a particular framework so that we can seamlessly develop this system. Otherwise, eventually it will be a mess. Even Indian government, if you will go on Wikipedia, you will see that they use a particular framework to develop all these systems. So the concept of system engineering can be applied to any vertical. We will be talking specifically about ADAS system. So we use a V model methodology. Till now I was talking about the design part, the technical part, which is basically over here. But actually how it works in the industry is we capture the requirements of the customer, of all the stakeholders. Based on the requirement, I design my system. Then there is an inner V loop inside the V loop. I design my system, I go into the details design, I do the virtual testing like the Unity game engine. I again do it till the time I feel that, okay, now it's time to deploy. I deploy it, I perform a particular testing using the deployment. Over here, the concept of hardware in the loop comes. Then I perform the module integration. If you will see, there are a lot of companies in India, specifically Mercedes and even Honda is using these space systems. That lot of hardware in the loop systems are today developed in India, OEMs or even in vendor companies to design and verify the system. So this concept has been taken from the software engineering, and we have a module integration test. Then we have a system subsystem integration test, and once it is validated, then the system is accepted and deployed. So I will give you one example. I want to design the adaptive cruise control. I will take the requirements from the ISO standards. I will take the requirements from the customer. Then I will functional decompose my requirements into functional requirements and non-functional requirements. Functional requirement can be system has to be stopped 5 meters before the obstacle. And non-functional requirement can be the usability, how it is easy to use the system, and robustness. And then we can talk about interoperability. So how I can use the system, how I can design the system based on my requirements. Once it is done, then I will deploy it, will verify with my virtual model, will verify it with my requirements, and then the system will be accepted, and then eventually it will go into proving ground testing, proving ground to perform the testing. So if I see the high level view, I need to design the context, usage, realization, and validation. The concept is don't reinvent the wheel. Now I will talk about companies which are providing these systems. So except Speedgoat, I have worked on all these simulators because I have designed a simulator for Millbrook, and then I designed a simulator for Cranfield University. And these different companies provide the real-time operating system. And this is quite important. Why real-time operating system? Let's say, take an example. You are doing a testing for airbag. And now I want my particular output to be delivered in a particular time. It should not take more than that time. That is the work of real-time operating system. It defines a particular time and answer will be generated in that particular time itself. Otherwise, if airbag is activated bit late, it might cause an accident. So that's why real-time operating system. Then you have physics engine providers. You have IPG car maker. You have VI Grade. It's an Italian-based company. And then you have MATLAB. So in the hardware in the loop, you have virtual plant and the real controller. In the rapid control prototyping, you have a virtual controller and the real plant. So what I can do in the virtual plant and the real controller, I can use virtual plant as IPG car maker, which is integrated with the MATLAB. And the real controller you can set up by yourself using Texas Instrument or NVIDIA or NXP Semiconductor. And then you can change the controller. For example, if I talk about power steering, I can change my torque map and see the effect on the steering feel. Then the rapid control prototyping, I can change the controller, virtual controller, and see the effect on the real plant. Then software in the loop, what we have developed, virtual controller and virtual plant, and then the subjective testing. So this has really helped us to make the development economical, and we don't need to use now the prototyping concept again and again. This is my work I did with Cranfield for the power steering group, and I was designing the electric power steering system, and this is the hardware in the loop I used. A vehicle simulated framework as a DSpace real time, and the MATLAB Simulink and the car maker. It was connected further with the real-time processor board, which is further connected to the sensors and actuators, and this is a device under test. So this is quite important to understand the hill configuration over here. And then we were using the actuators from the Bosch Rexroth. So the concept is, first define your project, determine your stakeholders, determine your requirements. Once the requirements is set up, then model the project. I am also giving you the exact questions how to define your project. Your questions should be answered if you want to describe your project context. All these questions should be answered. What are the 3 important goals? What are the project participants? How does the background situation look like, and what goals does not project should pursue? And there is a 1,000-page, 2,000-page document just for this in companies because there is so complex systems. And then the stakeholders, and then the requirements. This is a particular modeling ADAS system, how it should be done. The whole technical work, what we were discussing earlier, is done over here. First is start the project context based on these questions, determine the stakeholders, retrieve their concerns, extract the requirements, model the project, During the modeling, calculate the use cases. What Arjun was talking about. What are the possible use cases? How the customer is going to use all the use cases, even the apps you are using, Zomato or Swiggy, they also have developed the use cases before designing the software. Once the use cases are defined, then you have to follow a particular architecture. Once the architecture frameworks, now there are different architectures, what I was talking about, like DODAF, MODAF, which has been taken from the defense. And then there is 4+1 Kruchen, there is Zachman. Then you have to develop a UML diagram and the SysML diagram. So this can be done in a real time using various softwares called IBM Rhapsody or Enterprise Architect, and then there are real time open source also SysML diagrams. And once that architectural framework is set up, then you have to design your system. It should not be like that you are directly starting designing your system. It is not a proper way. Even if some of you over here are from Formula Student teams, this should be your process to design the Formula Student car. That's what they look for exactly. That are you able to actually cover everything, what customer wants or what stakeholder wants. Now there are modeling languages to develop these diagrams, Unified Model Language or SysML, and you can go to this reference of OMG group where you will get to know about UML diagrams. In a high level, any element is comprised of business, behavior part, structure part, and requirement part. Any element, and that's how we integrate our system. And then we have a particular view. Now, business architecture view is important for the management stakeholder. Data architecture view is important for the data scientist. Application architecture is important for the integration guys. And technology architecture is important for the guys who are developing the controller and the system, deployment system. So you have to define these architectures, and these architectures are defined using these languages, UML and SysML. So that's how our ADAS system is developed. This is a particular diagram of a software called Enterprise Architect developed by Spark System. And you can run it in real time. You can actually integrate it with the Simulink using the functional mockup unit and API, and then you can run it in the real time. Okay. So this is another Department of Defense architectural framework. Over here I showed you one particular architecture. Over here there is different architecture of DODAF. You have a project viewpoint. You have a capability, operational, services, system, standard, data and information, and all viewpoints. So this is your actually how the ADAS product looks like. It does not look like a code. Everything is behind that. This is how the whole system will look like. And all organizations uses this. You can consider viewpoint something like you have to take an image of a particular mountain. You are standing on the north end. So that's your view. And someone is standing on the south end, that's his or her view. So the view will change depending upon the stakeholder. Now I will talk, this is the last slides, and then we will open for question and answers. These are the recommended softwares and the languages which you should know while designing the ADAS system. At least some of them you should be perfect in. Python and TensorFlow used highly for AI and machine learning. C# for Unity game engine. C++ is specifically used for deployment of C and C++ for deployment of codes and development of software. And then MATLAB is for the integration purpose and performing the testing. Vector is used for CAN communication. IPG CarMaker is used for physical designing of the engine system, vehicle physics system. DSpace Control Desk is used for rapid control prototyping. ROS is used for communication. AutoWare is an open source which is based on ROS. And then Carla again for the visualization. So you should know the basic concepts eventually if you want to enter into the ADAS development or smart mobility domain, which is quite different from the engineering curriculum what I was studying during my bachelor's in India. And now the things are changing, and hence you have to understand a complete new perspective. And we have also showed you the demonstration how we have done it. We have used MATLAB and we have used C# for that. And now we are further planning to integrate it with ROS systems and other systems also. So it's quite important to recommend these languages. We are actually planning to putting some free courses also on vibrations and control, applied vehicle dynamics and introduction to ROS with C++ in next year. You can go to this link and subscribe to the channel, and I'm also planning to upload it on my website so that you can actually directly go over there. And these will be free because I believe that the basic fundamental knowledge should be available open source in the open source manner. And after that, for the development, things changes because then you are actually using the tools which are quite expensive. And some of these tools are quite expensive. MATLAB is quite expensive, DSpace is quite expensive, IPG CarMaker is expensive, Vector is. Rest of them are open source. Recommended lectures: control lecture from Brian Douglas, control lecture from Steve Brunton, and self-driving course with AutoWare and ROS by Apex AI. We also deliver some courses which we go in very depth, and this for vehicle dynamics and control with MATLAB, automotive power electronics with MATLAB, computer vision. And for hosting them, please inquire at this specific ID. And then this is a university package where we actually want you to get acquired to the complete ecosystem. You are having an online course, you are using our experiment toolkits, you are changing the things, you are studying the course, and then you are having a technical mentorship. So this is quite important, and thank you for your attention. I believe I shared a lot of stuff with you in a very short duration of time, but just to realize actually it works in this way. The European and the whole American universities, even the organizations, they're working quite a lot and the pace is quite high over here. And we need to set up certain courses and baseline to learn all these concepts. And that's what AKAR is focusing upon to develop this ecosystem. That's why we also, for this year, we collaborated with MATLAB so that they can support us. For next year, we are also looking forward to other companies also to create a whole ecosystem. So if you are interested in one of our seminars, do contact us and let us know. Till then, I will share the reference link in the chat now, and please start studying them, and I believe you will have a quite ample knowledge. And if you have any doubt, you can always contact us at our email ID. We are also trying to develop a web portal where students can directly contact us, and we will trying to help them in teaching these languages and helping them in development of these systems. So this is just a high level view, and for that's the last slide, and please contact us whenever needed. So thank you everyone for your patience, for your time, and I would in the end I would also like to thank Andhra Pradesh Skill government organization for giving us this platform and where we can share our knowledge of what is happening around the globe in India. Thank you.
Yeah, thank you so much, Ayush and Arjun. Yeah, of course, long webinar, 2 hours is a long webinar, so that's why the student count also decreased. But anyway, it's like a nice information what you have shared. It's the every slide what you have shared, everything I'm listening. So yes, nice webinar and very interactive webinar. But yeah, due to Sunday, many members having like Monday to Friday classes, Monday to Saturday classes again. If we conduct Sunday, yes, of course, will decrease the size of the students. But anyhow, so we got like 58 student, 63 students was the for this webinar the count. So and YouTube also like 50 to 60 students was in YouTube. So anyway, it's like 100 plus students was attended for this webinar. So it's like a, yeah, it's nice information, Ayush and Arjun also. So it's like a very good webinar.
Yeah, for
Like,
if we understand this because of Sunday also, and it's the last week of the year, so we can definitely understand that part. But it was nice to share the knowledge of what is actually happening around the globe, and we actually want that students in India start working on these things. The things which were conventional earlier now has been completely changed, and right now our only focus is awareness. And yeah, so if required, after 3 4 months, we can also host another webinar where for the universities. And yeah, you can students also can contact us anytime. I will share my email ID over here.
yeah, yeah, of course. So once again, thank you so much on behalf of APSSDC and behalf of CGM Dr. Ravi, because due to Sunday he is with his family. That's why he didn't attend it for this webinar, and also Prithvi also was not very busy. Definitely will conduct more webinars regarding on this. Thank you so much. Have a nice day.
Yeah,
Thank you, guys.
if any students have questions, they can ask us. Actually, we didn't have
Yeah,
a
yeah. Many
question.
members was asked questions while you are telling the question. That I'll ask some questions what they asked in chat box. Just I'll read out and just give the answers. Maybe if they are in webinar, they'll just listen what you're asking.
Yeah,
So, is it possible to control atoms by a controller? So, one question by Harsha.
is it possible to control?
Atoms by
Uh,
controller.
I have never used the Atom ID, honestly. Uh, so, but I believe we can. Do that, but I need to check that. It depends upon the API actually, how to set up the API between them. But if you want to cross-platform any two processors or any two softwares, whether they are able to do it or not, you can always use a functional mockup unit, which is like extract the variables. You can put that in Excel file or XML file, and then you can use the other software to export that variables into that. So that is always a possibility.
Okay, and another question that what about vector?
So Vector, I will share the link. Vector is a company, Vector Informatic, which works upon the CAN systems, CAN FD, and network across the communication bus in the car. So I will share this thing, and I would also like to tell this. One second, let me find the link on that.
Yeah, one more
Yeah,
from
I've shared it now.
Shrikant, that is
So
it possible to hack the control system of the car?
okay, no, now I think now I will talk about that. So uh, there is one specific this CAN protocol. It was developed by Bosch, and it has been set up in such a manner that it is given with lot of cyber security across the data bits. So the core data is not transferred. It is also bounded by the various other security protocols. So it's not easy, and you need a particular file to understand the which data is of which sensor. If you will just see the file of CAN file, it is just numbers. You will not understand anything. It's in the hexadecimal format. But there is one file which is an intellectual property of all the companies, where they have related the hexadecimal format of a particular sensor signal to the actual sensor value, where you can say, okay, this is the steering value, this is a throttle value. but you will never find that intellectual property document anywhere. It's of company's property. And, I will share the CAN protocol PDF or something, CAN bus, where you can see the cyber security part and how it is binded with the cyber security. And the vector, you have to import file from the company to actually synchronize your hexadecimal data with which sensor value it is.
Okay, that's all about. I think that the question's done. So yeah,
Okay, then thank you for everyone again for your time. Wish you a happy new year, and
yeah,
yeah, I hope to see you next year too.
yeah. Same to you. And we'll meet for next webinar definitely.
Sure. Okay, bye.
Thank you so much. Bye.
Thank you so much.